Okay, I think let's start. My name is Eddie Schipper. I work for the Netherlands Enterprise Agency. In the Netherlands, optics and photonics is a key enabling technology. In the Netherlands, there are many exciting new optics and photonics technologies in development and also commercially available that could play a major role in tackling the many societal challenges, environmental monitoring, structural healthcare monitoring, and so on. Taiwan has a big, impressive high-tech industry, and optics photonics is also in Taiwan of growing importance. Again, to tackle the many challenges in Taiwan due to, for example, climate change, earthquakes, urbanization, and so on. I think that there are many opportunities to work together to get in this way to even better solutions and bigger business opportunities. 3 years ago, some collaborations started already. We in the Netherlands had the intention to visit Taiwan in March this year. Unfortunately, at the last moment, due to COVID-19, the program in Taiwan had to be postponed to October. We still hope to visit. We did not want to wait, and for that reason, we tried to keep the spirit alive with the start now of 3 to 4 webinars. This is the first one. It's all new for us and also for me. Let's hope it works. The first session will be completely related to fiber optic sensing. Fiber optic sensing was one of the first optics photonics topics that we found 3 years ago as a field with a lot of opportunities for collaboration. Some shared projects started already, and we think that there are still application areas that wait for this technology. Hopefully, in the next 2 hours, we get a step closer to find these opportunities. We will have in the coming 2 hours 8 impressive speakers, 4 from Taiwan and 4 from the Netherlands, on 4 different topics. I think that's what we can see now. We see the different topics and the speakers already. And then something for the attendees. You have the opportunities during the session to use the chat function to ask questions. At the end of each subsection, so we have 4 subsections, we will come back to these questions. So I think now let's start with the first speakers of the first subsection, disaster prevention. So I want to introduce 2 speakers, Dr. Huang, technical consultant of CITPO Technologies, and Rick Knoppers of Somni Solutions. So let's go to their presentations. So let's start.
Good morning and good afternoon, depends on where you are. My name is Huang. I'm representing CITPO Technologies in Taipei, Taiwan, to talk about photonics applications for disaster prevention. What we do is mostly concentrating in the development and applications of FPG sensors. Most of the applications are related to ground behavior or any disaster that may occur in the ground. To start with, I would like to give a very brief introduction to FPG, what it is. Optical fiber Bragg rating is the full name. It's basically a change of sections, small section, about 5 millimeter long optical fiber. It's a refractive index periodically. The optical fiber has a diameter of about 250 microns. It's about the size of a human hair. The change of this refractive index periodically is similar to put your fingers, your whole 5 fingers on your arm and expose the arm under the sun. After a while, if you take off your hand, the parts that's uncovered will turn dark, and its covered part will be light. sort of like this grid pattern in this slide. Except in FBG, we may have about 10,000 of these grid concentrated in about 5 millimeter length. The spacing between the lighter and darker part is we call it capital lambda. And when we insert laser light into optical fiber, when it encounters FBG, part of it will be reflected back. The wavelength of the reflected light, lowercase lambda b, is related to the refractive index and the capital lambda, the spacing of these grid patterns. The N, refractive index of fiberglass, which is pure glass, will be very stable, very constant value. And that makes FBG a very ideal strength sensor, because if you stretch the fiber either by force or stress or induced by temperature variation, there will be a change of the reflected wavelength. So that's the basic idea of FBG. But the advantage does not stop here. We are able to put more FBGs on a single optical fiber. In this case, you see at least 5 of those. Because if we space, we make every one, FBG has a different domain of capital lambda. And that means the reflected light will have a different range of wavelengths. That we can differentiate the source of the reflected light just by the value of this wavelength. Typically, we now are able to put about 6 FBGs on a given optical fiber. The advantages of FBG sensors are many. To begin with, it's immune to electromagnetic interference and lightning because there's no metal in there. It's all transmitting signal with light. There's no issue of short circuit, and the material is very stable and durable, made of glass. It's small and flexible, size of hair. Capable of partial distribution. That means we can put more multiple sensors on a given optical fiber. The signal has very low attenuation. We can now easily transmit signals, very good quality signals, for about 10, 20 kilometers without any concern of losing quality of the data. So potential applications, of course, we can use, if I just use the FBG itself, it's a good strength sensor. It has a resolution of 1 microstrand. Or a temperature sensor. If we just isolate the stress out of the sensor, we will have a resolution of about 0.09 degrees Celsius. And beyond that, we can couple the FBG with mechanical devices to turn into different types of sensors, pressure to measure pressure, force, displacement. Very similar to the case we use strain gauge, foil strain gauges and then coupled with mechanical parts to make it to load cells and pressure sensor. Very similar. But in addition to that, we can deploy the sensors in arrays where multiple sensors can be connected to a single optical fiber for profile measurement. That brings into a lot of applications, especially to monitor ground conditions. And not just that, in this array, we can mix different types of sensors to measure different physical quantities. For example, we may have pressure sensors and displacement sensors. If they're all made of FBGs, the readout unit only distinguishes the wavelength. Doesn't matter what you're measuring. Or we can measure inclination plus displacement, so far and so on. It's only limited by your imagination. The next few minutes, I will introduce what we have done. Just a few examples. For example, this is monitoring of the strain in a tunnel lining. In this case, it's the Shien-Kuei tunnel line, MRT, one of the newest and most beautiful tunnels in Taipei. you have a chance to visit CITPO, you have to take a look at it. And this is close to the most beautiful subway station, Da'an Park subway station. What you see here is a result of about more than 2 years of monitoring, 800 days. The very synchronized variation of strains, because they reflect the temperature change, summer, winter. But I'm not going to any details, just to show, other than showing you the data. And if we're more interested in natural disaster, this is a very common kind of disaster in Taiwan, is slope failure. This is where we, on the right side, we're installing FBG-based inclinometers to measure the ground movement-induced inclination. On the left side, you see comparison between FBG sensors and manual sensors. The green curves is the manual results, manual readings. The red curves is from FBG. The numbers may be different because they're at slightly different locations, but the trend is similar, very much the same. This is where we use 10 pore pressure sensors, measure water pressure in a single borehole from depth of 15 to 55 meters deep with the 10 pressure sensors. And this is the result of on a slope in Alishan, a very famous resort area in Taiwan during Typhoon Marakat. It's a very severe typhoon. In this case, just to give you a very basic sense, the pore pressure increased by as much as equivalent to 30 meters of water level, which is about 10-story high. So the increase of pore pressure is very extreme, and that's why it caused a lot of slope failures in that region during that typhoon. That also tells you the importance of monitoring. This is another case of a very common problem in Taiwan, ground subsidence, because of the groundwater pumping. In this case, we put in a profile of expansometers. This is measure the vertical movement and pore pressure sensors like we showed earlier. But this in a borehole that's 100 meters deep. We have 10 meters different distance between these sensor sets. The left side is the movement of the ground at different depth. The right side is the pore pressure or water pressure versus depth. You see the dashed line is if we have no just static pressure. If the water pressure goes up by its own unit weight with depth, you should have this linear shape. The fact that our measurements are lower than that shows you the result of excessive groundwater pumping. And at lower level, the measurements higher than hydrostatic means we have artesian. And that tells you why people thought this was a good area to pump groundwater, because there's just abundance of groundwater. But anyway, that's the part of the study to understand the nature of ground subsidence in this region. This is a newer subject, very hot issue in Taiwan, is offshore wind turbine or wind power development. We used our tilt sensors as a simple, these are the picture of the tilt sensors to measure the vibration or oscillation of the meteorology mast. This is a reading taken during a calm season, no typhoon, no strong wind. If we do a Fourier transformation, we see two primary waveforms. One concentrated about 0.55, or the other way, one is about 1.35. In any case, these are very low frequency vibrations. And that prompted our desire to get into low frequency accelerometer development with our partners in Holland, Somni, who will make a presentation after this. This is to measure the relative tilting or movement of the railroad track, the right side versus left side. These are, on the left, you see the railway sleepers, and we have sensors on crisscrossing the track. right side is a picture of sensors, and the down part of it, lower part of it shows the reading for a period. It shows that the readings are fluctuated within plus minus 5 millimeters, way within the safety limit set by the railroad company. This is also related to rail, but I'm not allowed to give you the details other than that. There's a fault movement near crossing this railroad track. That movement causes the all kinds of movement, piles in the ground, pile cap structures. So in order to provide the values for their analysis, they would like to know is there any relative movement between the pile cap and the 4 piles in the ground. So we developed a sensor that measured inclination in 2 directions and extension, and put it in the pile cap. So we just did this 2 weeks ago. So we're still collecting our first set of data. So just to show you the field setup or the conceptual setup. And that will be my presentation. I'll leave the next part to our partner, Rick from Somni.
Okay, then maybe we can go now to Somni.
Well, thank you for introducing me. My name is Rick Knoppers. I do work at Somni, and we do a Global Stars project together with some other companies, and one of the companies is CITPO, who had just a very nice speech and very clearly explained how the FPG sensors work. And we also have a combination in work with TNO here in the Netherlands, which is a big research institute. I would like to tell you a little bit about what we are doing. First of all, I would like to start with why should we use fiber optic sensing. Then I would like to tell you a little bit more about what Somni is doing in fiber optic sensing. And I would like to put some extra attention on the robustness of the fiber optic sensors. I also would like to have a little section about what we are doing in the Global Stars project, because I think it fits very nicely in this topic. And then I would like to close with talking about the test locations for the low frequency accelerometers that we try to develop in the Global Stars project. So first of all, why fiber optic sensing? Well, if we have big assets on the world, like big buildings and bridges and things like that, we like to make decisions based on actual measured data, of course. Very big topics in this world is predictive maintenance. So if you can measure the system all the day and you know what's going on, then you can do the maintenance at the moment you really need it. And another big topic is the extended lifetime of big assets. If you can prove that your bridge is still stable and it can hold for 10 more years than expected, that is a lot of money. Because everything has to do, of course, with money always. So reducing the cost is a big goal of measuring on these big objects. And of course, increasing the safety and the topic of today, preventing disasters. That is, of course, the most important one. Well, to start with preventing the disasters, we probably all know this bridge. This is the Morandi Bridge in Genoa, Italy. And about 2 years ago, it completely collapsed. That was a big disaster and quite unexpected for a lot of people. But on the other hand, they knew already that there was things going on with that bridge. They are at the moment building a new bridge. This is an image of that new bridge that's being built. It will be opened in probably July. And this new bridge is equipped with a lot of sensors. And part of the sensors are made by Somni, and they are on every pole of this new bridge. So we make tilt sensors, inclination sensors for this bridge, 72 sensors, and they are placed on the top and on the bottom of the poles in 2 directions each. That was a very nice job. When they're installed, they must be cabled, of course. So there is a cable going to all the sensors. And then at the left side, there is a electric cabinet in which there is an interrogator looking at these sensors and reading their actual values. And this electrical system is in an area where you can easily do maintenance. And this electrical system could easily be replaced if necessary. Well, the big question is, why do people use fiber optic sensing for these kind of applications? And that all has to do with robustness. It is a fact that the fiber optic sensors are extremely robust and have a very big lifetime. And that's a topic that I would like to address a little bit later again. Another thing that Somni is busy with, for example, we make a lot of sensors. We also have sensors in the medical field. We make sensors for defense, hydrophones, very little pressure sensors, things like that. But I wanted to pick out one because I think it's very interesting. That are sensors that we built at the moment for a big science project, and it's called ITRI in France. We probably all know the ITRI project. It's a very big nuclear fusion project taking place there, in which nearly all the world is involved. China, Russia, the USA, Europe, Japan. All countries are involved in that big ITER project. There's a lot of radiation there, and it's a lot of vacuum parts. So we took our one of our types of sensors, the 80 picometers per G sensitivity sensor, a standard sensor, and we modified it for vacuum compatibility and made it radiation hard and made it stable up to a temperature for 160 degrees Celsius. At the same time, they also needed temperature sensors, so we also developed vacuum compatible radiation hardened temperature sensors, which can range up to 300 degrees Celsius. These sensors must be ready in September this year and then will be shipped to the ITER project. And as you can imagine, there's also in this case a very big issue with reliability and robustness of the sensors. So I would like to give that some extra attention. All our tilt and acceleration sensors are built from one motor block of steel. And in that motor block of steel, we create what they call compliant mechanisms. To explain that a little bit, I did put down this picture of this scissor-like clamping thing made of one piece of plastic in blue. And well, you all know that kind of products, I think, but it's a product made out of one piece of material. And still, you can make some movements with it and clamp something with it. Well, our sensors are built in the same kind of way. I put a picture in at the right picture, which is not our sensor, but something I found on the internet. But that's also a compliant mechanism. So it has elasticity at a lot of points, and then you can make very defined movements with parts of that solid block of steel. We make very small movements. We only make movements of less than 20 micrometers. That's about a third of a hair thickness. And the stresses in our materials are during its lifetime very, very low. It is always below 0.5% of the maximum load allowed for that type of material. So the material should survive for not 30 years, what they most of the time ask for a lifetime, but it should survive for 100 years. That's no problem at all. So we have this one donor block of steel with compliant mechanism creating the sensor, the working principle. And then we have, of course, to bond the fiber to this mechanical block. That's always a difficulty, but we found ways to do that very secure. And we now have bonds that are perfectly okay for a long lifetime for higher than 200 degrees Celsius. So due to the construction of our sensors, the Somni fiber optic sensors are extremely robust, reliable, and they have a very, very long lifetime. And that is very important for most of our customers. So I'd like to change the topic a little bit now and go to the Global Star project. It is a project that we do together with CITPO, the previous speaker. And in that project, we try to develop a very low frequency, high sensitivity accelerometer. Based on the FPG technology again, the sensitivity should be higher than 100 picometers per G, 1000 picometers per G, sorry. And the resonance frequency should be not lower than 300 Hertz. The low frequency we'd like to go to is about 0.1 Hertz or even lower. To be honest, we think that our sensors are able to work up to 0 Hertz, but we still have to prove that, of course. This is a very, very sensitive sensor. So if you transport the sensor and put it on a table, there's a big chance you will damage it. So we put ourselves the demand that we should put a locking mechanism in the sensors to be sure that you have a safe transport and be sure that the sensor is alive when installed. We made already some prototypes. These are the prototype sensors. On the left picture, you see the locking mechanism, which is very simple to use. And you see a little bit how the sensor is built up. The sensor is already being tested at TNO. We did do 2 types of tests. One test for the little bit higher frequencies, that is the left testing area. That's a very big shaker. And we did shake our sensors there. You can see them in the middle of the plate. And at the right side, we tested even lower frequencies on a universal testing machine. And that was quite okay, but still can be improved. Something went wrong there, and if you see the test results at the right bottom, then you see that the sensor 2 died, or one of the FPGs broke, and that was because there was made a mistake in programming this testing machine, and the sensor got about 5 times the allowed maximum acceleration that it should have, so one of the fibers broke. But what you see with the results is that they're all, the good working sensors are above 1000 picometers per G, which is what we intended to do, so that's very nice. So we think we have very good test results with the first test. At the moment, we are developing a new generation of sensors to get better results and maybe also a little bit lower price. That would be nice. And this test will be done again at TNO with the new sensors, and they will try to improve the testing a little bit so that we have better results. And then a new exciting period will start, and that will be testing together with CITPO in Taiwan. And I think we found the best test location and the most exciting test location you can ever find in your life, because we are allowed to test this sensor on the golden sphere that is in the Taipei 101. The Taipei 101 is has been the biggest building in the world for about 6 years, from 2004 to 2010. It is 508 meters high with 101 floors. And the Taipei 101 is, of course, built in an area where there's lots of earthquakes. So to protect it against these big shocks, they put in a sphere at the top with a mass of 728 tons, with all supported by dampers around it to dampen the vibrations in the building and to, let's say, eat the energy out of an earthquake. So we are allowed to put sensors on the golden sphere, which is really the best marketing place in the world, I would say. There is already a lot of sensors in the Taipei 101, also frequency sensors for low frequencies, and they are measuring there day in, day out, all day, all the year. What you see at the left is the measurement of these sensors at different floors during the earthquake in Japan at 11 March 2011, the big earthquake in that period. And what you see at the right are power spectral density plots during that earthquake in Japan. These spectral density plots are very, very important plots, because in that plots you can see at which frequencies what amount of G-forces were put on that building by the earthquake. So looking at these spectral density plots, I put down 2 here. The left one is during that earthquake, and there you can of course see in very big detail what shock has been on that building and at what frequency, and you can compare that with what you know of the building and calculations, and see if the building is still safe after the shock. So that's very important. At the right side you see a graph which is a normal day spectral density plot, and in that plot you can see also of course the resonance frequencies that are in that building. And that is a very, very important point, because these resonance frequencies in the building, they should not change over the years. So they should stay the same. If they change, then something is changing in the construction of the building. It's either the mass that's changing then, and that you probably know, or it is the stiffness of the construction. And when the stiffness of the construction is changing, you know there is something going on with your construction which is not good. So by looking at spectral density plots on these very low frequencies, you can see the day-to-day health of your building. And that is why we are now together with CITPO working on the development of this very low frequency FEG-based accelerometers to measure these kind of vibrations, and do that with a system which has a very, very high reliability for a long period of time. Okay, this was my presentation. I hope I give some information that you can use, and would like to thank you for listening.
Okay, many thanks. So we had already 2 interesting presentations. I see there are also some questions already. First of all, I want to say to all the participants, use the Q&A for the questions. And if you have a question, then ask the question to everybody. So not only to the panelists or to the host or the speaker, so that everybody can see the questions. Now to the questions that are raised already. First of all, to CITPO. The question is, these are very interesting projects in Taiwan. but do you also have already projects outside Taiwan? And if not, do you aim at projects outside of Taiwan?
Well, I think one of the strong attractions by working with Somni is, well, of course, we're interested in the outside of markets outside of Taiwan. We have done small scale projects in Singapore, also in China. We are in the process of signing a contract with the research institute, a major research institute in the U.S. So yes, a lot of things are going on, and we are extremely interested in the international market.
Okay. More or less a related question to Somni. You showed already this exciting applications with the Taipei 101. But what kind of projects are you aiming at in Taiwan for yourself?
Well, that is very nice, of course, because we work with CITPO, and I think we together look at more areas where we can do look at low frequencies sensors on big structures. I think we still have to find that out a little bit together. But we are looking at also at a lot of other structures in Europe, of course, and mainly that is big assets like bridges and big buildings.
Okay. Let's see. Yeah, I have one question. I think then we can go to the next session. But I have one question. I see many applications are low frequency applications, especially what you present at CITPO. Is that for a reason? Is it something which you're looking for in these disaster prevention?
Yes. Again, we want to take full advantage of FBG sensors. The high frequency sensors are very well available. We have a lot of competitors, so to speak. I think the low frequency accelerometers will have a major market in the future, especially for large structures. As we have demonstrated in many cases, the natural frequencies are very low. And there's the conventional approach will be rather expensive. So therefore, I think FBG will be very competitive. Maybe Ray can help add more to this.
Yeah, we are also working with higher frequencies, but Bin is completely right that real high frequencies is not very interesting in FBG technology. But we do also look at railroads and constructions like that, which is also done by CITPO. And then you talk about a little bit higher frequency most of the time. So there is application with higher frequencies up to, let's say, 1,000 hertz, which are of interest for us, to be honest.
Okay. Yeah, I see a difficult question from the audience because there was a question about global star projects. There's a question from the Dutch side. It's more about funding for projects. I think when there are good ideas, we can always look into that. So that's a question I think I will answer. But it's a little bit too difficult now to get a complete discussion about this. Yeah, for the moment, I think we also for the time we go to the subsection number 2, which is a little bit related to this subsection, which is the session with Mark Jacobs of Optic and Dr. Yi-Heng from ITRI. And that's about fiber optic sensing, of course, and about structural health monitoring. So let's go now to Mark or Dr. Yi-Heng.
I will start, Eddie. So, hello everybody. My name is Mark Jacobs, as mentioned by Eddie, and I would like to talk about fiber optic sensing and then related to structural health monitoring. So before I go into the fiber optic part of the presentation, I just want to address a few words on the structural health monitoring science, the structural health monitoring itself. Just the reasons why we would like to do this. It was already mentioned by the previous speakers, but the tendency that makes ours are moving is that we move away from reactive scheduled maintenance towards more condition-based maintenance. So you actually can apply the maintenance when it's needed. It gives a better lifetime prediction, you can have better product development, and you can monitor the degradation of your asset over time. And a third important point, that critical faults are detected in an early stage, and that you can follow that and make some measures if needed for this. Now, when implementing a structural health monitoring system, there's some things you need to consider. First of all, it needs to have a long lifetime. It needs to be able to survive all sorts of weather conditions during this period. It needs to be very sensitive and reliable enough, so you can, because the changes that you're going to measure are very small, and you also need to measure those in a later period of time, at the end of the lifetime of the asset. And to be able to be cost effective, to make it all work, it should be easy to integrate. A lot of sensors are required, so the system as a whole needs to be looked into, the cost needs to be considered. If you look at the current trends today, I'm not completely sure about the numbers in Taiwan, but 1 out of 5 bridges in Europe is in poor conditions. Means that they are like at the end of the lifetime, and they probably are need to be fixed soon. And so new construction innovation projects, they start to more and more integrate the structural health monitoring solutions. And basically, it's important that a good structural health monitoring system can expand the asset lifetime and avoid failures that are very costly. Now, what has fiber optics to bring to this solution? Now, you're probably all aware of all these advantages that you have for using fiber optic sensors. But for structural health monitoring, I want to highlight a few of them. So you can have a dense grid of monitoring points, so it's easy to chain a lot of sensors together and make them all fixed to your asset. It's long-term stable. There are only a few parts inside those sensors, so they can last for a long period of time. Which is also can be far away from your measurement system, which is the most the big investment of your system. And this can be exposed to all kind of environments, because that's also a thing that's very important. Lightning, with weather, liquids, radiation, things that can occur need to be are easily dealt with fiber optic sensors. Now, if you look at a fiber optic system overview in general, you have a readout on the left, which can be stored away far from your asset. In this example, is a bridge. Then you connect that part with some cabling, which can be up to kilometers apart, because it's only light that goes to the cable. And then you're going to look at your sensors at the asset. They're completely passive, so there's no power required. So that makes it very useful. They're very sensitive, and they have a very low noise level over long distances, immune to all kind of radiation. And as said, they're very rugged, so they can withstand all the outdoor conditions, including lightning, for instance. Now, what has Optics 11 technology to offer to this application? Basically, we're focusing on 2 types of systems that we offer. The first is the NovaFAS, which is the most accurate and precise FPG system available. And basically, it's in the low end of like the low frequency measurements, so strain, temperature, and load, and it measures those parameters over time with a high level of precision. And on the other end of the spectrum, we have an acoustic emission system, which is looking at the high end, so when actually the cracks are occurring into the structure, so up to hundreds of kilohertz at the time, and that system is called Optimate. Now we have a broad portfolio of fiber optic sensors that we connect to both of those systems. The application experience to install them, and we can have a very reliable partner network that we can involve and we have to do the installations. A few words about the systems itself. So again, the NovaFAS, it's high-end FPG. And what makes this system unique is that it has a self-calibrating system. So each time we send a sweep of light into the fiber, this light wavelength is calibrated. So that means that there's a long-term stability over time. So it doesn't matter what the humidity is or what the temperature level is. The actual values that you measure, for instance, strain or the vibration, are actually the value on the asset and not some influencing on the system itself. And that's why you can measure the true conditions of the structures over time. If you look at the other system, the Optic, so again, it's the acoustic emission system that looks at real-time detection of structural events. So when you actually have a crack of concrete or metal, it creates energy, it's sound, the ultrasonic sound that can be picked up by these sensors. And you can locate damage from very early stages when it's actually occurring. And if you have multiple sensors in on your asset, you can also triangulate and determine the exact location in a very early stage. And then you can follow this fatigue and make sure that you can make the appropriate actions. Of course, if you install a system, you need the infrastructure as well. So we are as a system provider, we also provide the accessories and the other things that are required to make a full system. So the cable network, the place where you can store the equipment, the readouts, and also the access to the outside world, because you need to look at the data. If you look at the data itself, we provide a very basic portal that can look real time at your data from the asset, and I think this is quite interesting because if you have all your sensors connected into a network, you would like to have monitoring or like warnings when a certain threshold is crossed. So what we do, we have a local site which has the sensors and the data acquisition, basically the data goes to the data gateway and will be sent out to the cloud through either wired or wireless network. And from the cloud, it can then be accessed through a web portal, which you can look at your data real time, and you can customize these dashboards to the asset or to the type of sensors that you would like to monitor. I would like to discuss some of the examples that we applied these systems. So this is a bridge, the IJsselbrug in the Netherlands. Basically, this is the real-time monitoring of critical spots of this bridge. It's a concrete bridge, and we were involved in installing 35 strain and temperature sensors and measure this bridge over time. Another example where this is applied, this is in a cave, a marl cave in Valkenburg in the south of the Netherlands. And their question was to have real-time measurements on the stability of the cave. There are a lot of tourists going inside each year, and safety is of their concern, and they want to know whether there is any movement of the ceiling. So we installed 80 sensing strain strips, as you see in the picture. Which see whether the ceiling is stable, yes or no. Of course, with the dashboard as well. And one of the part of the involvement with Taiwan, so we also have a Global Stars project. We are monitoring, or in the process of monitoring a floating trackbed. So that is part of the foundation of where the metros go into the tunnel for the MRT in Taipei. And basically what a system will do is to monitor the vibration levels of the floating trackbacks in the tunnel and see whether the structure behaves as is designed and whether there's any resident vibration goes into the environment. And on top of that, we're also applying some of the acoustic sensors to the rail itself, so to see if we can monitor the passing metros as well, looking for flat spots on wheels or condition monitoring on early fatigue and bearings. Now, the last slides are about the Optics 11 as the company. So we like to consider ourselves as a one-stop shop on monitoring parameters. That means if you want to look for high-end acoustic emissions or high acoustics, you might measure of vibration, all the way down to strain and load and tilt sensors on a low frequency with a long and stable period. We have a solution for that. We make everything ourselves, so the whole system will be built up, so we have complete control over the complete setup. Yeah, basically, we are based in Amsterdam. We have a small R&D office in Dublin and some distribution network all over the world. And yeah, we are at 55 people and heavily growing and looking forward to see what kind of challenges we can solve in Taiwan.
Let's go to some questions. Maybe in the meanwhile, you have to Optics 11. I see also that you work a lot on the visualization and with software. Do you think the software development becomes more and more important?
Basically, that's something that we recently started, and I think it's a very powerful tool at the end for the end user and for the asset owner to have real life access to the data. So of course, it's very technical and very difficult to install make sure that everything works. But yeah, basically the question of the asset owner is just how is my structure actually doing and what is actually happening at this time. And by providing this in a cloud-based solution with some basic parameters that you can actually evaluate this every time of the day, and in some thresholds being installed so that you get a signal that actually some values are crossed. We think it's quite powerful.
Okay. And about the project, you have a project also in Taiwan, which you're working at. What are the next steps there for this project?
Now, we got a bit delayed, of course, to the whole COVID-19 part as well, and also to get the approval to go into the tunnels. But it seems everything is now lined up to go in there. I think in October, we're going to install the first set of sensors. And basically, we're going to go there 2 times. So
my topic is about the prospect application of optic fiber for corrosion in structural health monitoring. And very quick. So why we want to do the structural health monitoring? Because sometimes something will always happen, like aging, like permanent, and cyclic loading, like environmental effect, and like minor earthquakes. But what we do now, even we have so many monitoring technology, so many sensors, generally people always do the visual inspection. However, visual has some weakness like time consuming and expensive. It's periodic and service interruption and like subjective and prone to human errors. So that's why we do the monitoring. This year we have a new project about make the structural health monitoring through on digital twin. It's an idea. Let's make a real world and a digital world connected together based on a digital sheet. Like we consider design operation like IoT data, like analysis and something machine learning and something IT integration. And this year we take a oil tank as a sample, and we use the LiDAR scanning the profile and to diagnose which one is deformation and which one is corrosion. And we will show in the digital world. In that topic, we noticed that corrosion happen all the time in Taiwan, much more than deformation and other problems. So we have a new idea because here we're trying to sharing some new idea, and we can see the corrosion problem in Taiwan is very serious, like automotive corrosion, like pipeline corrosion, something environmentally induced cracking, some MIC, and something CUI. This corrosion causes a lot of cost in Taiwan, especially in petrochemical industry. So, and ITRI, it took a lot of effort. Our department, our division, put a lot of effort to solve this problem throwing some new old skill like NDT technology, like corrosion monitoring technology. In NDT, we find out the location according to the risk matrix, and we do a lot of like UD sensor, like a laser scan, like RT, and we do something ferromagnetic analysis and implementation. And about the monitoring technology, we sometimes always put some ER probe into the pipe, or we made some online monitoring from on UT to do the monitoring. However, this technology is not good enough. And last years, we had some cooperation with Mark, and we noticed that fiber optic is a very powerful sensor to do the monitoring. So we have a new idea start from the mechanism of corrosion. We can see we want to protect our structure not to be corrosion. So we have something pen system under our structure. We can see the anoxygenic, like epoxy, like PU to anti the UV and to the water resistance. However, like I just said, it's always happened, and aging and something degradation is always happen on the cracking, like blistering, like cracking, like rusting. We notice that all this phenomena will change something what fiber can censor. Like we can, the will cause temperature change. Will change the temperature on the surface. That will make some deformation on the surface. That's we want to do through fiber optics. However, and we do something research. There are already have some sensors designed through optic fiber, like to do the monitoring about environment parameters, like wave theory, like volume expansion, or like tensor stress relaxation. However, these those sensors only designed through the corrosion mechanism. They notice at a polynomial and they do the monitoring. And as I said, ITRI put a lot of energy to anti the corrosion. So we already know the pen system design. So here we have a new idea. Can we do something design through the pen system, and we can control the corrosion mechanism, and we can decide what phenomena should be shown and should be monitored. So we have a new idea, and to put it all together in a new cycle, we can do new design for the pen system, and we can, based on this design, to design our new monitoring system through on fiber, optic fiber. And I'm sorry it's a little rough here, and this is my presentation. Thanks for your attention.
Many thanks. So it was a clear presentation, so it wasn't a problem. Yeah, questions. Yeah, I've one question myself. You started already that you are going to for this digital world, and digital world means that there is a need for sensors, all kinds of sensors, and fiber optics sensors are one of them. In the application, you are looking very much to this metal corrosion and paint and so on. Do you also have applications in concrete, or did I misunderstood it? Is it also in concrete?
Yes, we do. We do some research to the concrete, but for us, the concrete we in experiment, the concrete is not how to say that. We can have some change in chemical or in physical in short time. So we just start at half a year, and experimentally we can adapt concrete into our experiment. But yes, we want to do that in concrete structure. Yes.
Okay. Thanks again. I think also due to the time, we lost a little bit of time. We go now to topic number 3, and that is the aerospace topic. And again, 2 speakers, Dr. Tung from Ars Navigation and Rolf from Technobis. I don't know now who starts. Okay, yep.
Okay. Hello, everyone. I'm Tung, and this is the name of my company, Ars Nav. Should be a good hint of what product we are making. Ars Nav is a young startup just about to launch its product this 4th quarter. Here on the left is an intuitive view of the market trend that we perceived. Given an enabler that's working effectively, we believe there is great market vacancy for high performance gyro if provided at affordable price. So what exactly Ars Nav can offer and how? Unique design is one of the key factors, and efficiency in process and integration are the other 2, to which the industrial infrastructure here in Taiwan does benefit. We also plan to have more key components made here in Taiwan. Our Precision 100 series is engineered for general navigation, stabilization, and precision attitude sensing feedback. This one is scheduled for launching this October. Here's our higher sensitivity series, intended for deep, autonomous, and long-term operation. This one, higher sensitivity fiber gyros. Okay, let me quickly explain to you how the 2 most important parameters of fiber gyro correlate to the navigation accuracy. First one is the bias of a gyro. It's the angular rate output when the sensor is actually in static. Ideally, it should be 0, but usually they are not. So you can imagine how it actually inherent and accumulate to large angular errors if the task operating hours increases. Assuming that the deterministic part of the gyro has been calibrated out, say, by accurate modeling, then you will see angle random walk as the fundamental limit of your accuracy. For example, here is our gyro, which was tested to have the angle random walk parameter of 0.02002 or 2 milli-degrees per square root hours. Then how to use that in practice? You just multiply this parameter with the square root of the operation hours. Then it will give you the cumulative error error, cumulative error in angle at the end of the task. Now, nowadays, passenger jet typically has cruising speed approaching 1,000 kilometers per hour. Say for 10 hours operation, then you can travel 10,000 kilometers, which is about the distance from Taipei to San Francisco. Which means with an accurate fiber gyro like this, you can actually do that reckoning flight without any help of GPS signals. And you can have pilot go to sleep over the whole cruising hours, and just wake up in the last hour or 30 minutes and take over the wheel for landing. So this is why the two parameters are important for navigation. As a quick summary, ArcNav are seeking applications that have outstanding features like these. And finally, thank you for listening, and let's keep in touch for more discussion on the applications. Thank you. That's all my.
Thank you very much.
Thank you.
Okay, so good afternoon. I'm Rolf Evenblij from Technobis, and I'm going to say something about fiber sensing in aerospace. And as the title says, it's about revolutionary changes in fiber sensing due to the use of integrated photonics. So we use optical chips instead of free space optics, and that has quite some advantages. It makes the devices smaller and cost-effectiver, and it increases reliability, and that's the basis for our involvement in aerospace applications. So I will start with giving some examples of projects that we do, and then come back to the project or to the products itself. Typically, we collaborate with partners in these projects where we develop and provide the modules, the fiber optic sensing modules. Our partners, tier 1 companies or other partners, they develop the sensor itself, the sensor assembly, and the electronics to integrate these devices with flight systems. So we have some commercial developments that we develop. We have some systems development that we do in collaboration with other partners as well. Sometimes in European funding programs, but also in commercial programs for other purposes. And then there is a lot of research that we do with consortium programs. So to start with the commercial ones, we are developing, for instance, just go to the next slide. A overheat detection system for a large passenger aircraft platform. In this case, it's the A350. And as you can see, there's not much to see on the right side of the slide. It's just a small device. It's a matchbox size, but it holds a lot of technology. It includes the optical chips that we use for the detection of fiber Bragg ratings, fiber Bragg rating sensors. And we deliver it, we implement it, in collaboration with the tier 1 company, and then put it in the aircraft. Now, one of the big advantages, like I mentioned earlier, of these optical chips is that they are very small, and that is and quite reliable, and that is of great importance to the aerospace. When we set out this development, the challenge was not so much build the device. Of course, it needs to be reliable and compliant to the aerospace environment. But what's also important is the possibility or the capability that to produce these devices with a high yield for a very long time. And that includes more than just building the device itself. It includes a complete development of your company, where it regards industrialization, volume manufacturing, quality system, etc. So this is one of the major challenges that we are facing in this development here. So this device is for OEM. We only provide the modules. The same system we are planning to put on the market as a standalone device, which is planned for 2021, next year. And the volume production capability that we are developing is about more than 10,000 in 2023. So we're anticipating a large market for these types of modules. Now, another example is landing gear load sensing. This is a system that was developed in a European program together with Airbus again and a tier 1 company called Magit. And it basically, it's the same thing as before. We are providing a module, a fiber sensing module. You can see a small image here of the system that is integrated in the aircraft. We provided this package, which includes an optical chip. Next example is structural health and usage and load monitoring. This is not an OEM development. This is the development of a commercial off-the-shelf product that is destined to be aerospace compliant. Where we develop this box, we collaborate with other companies or in this case, one specific company, the NLR in a lot of cases, where they develop the application and we develop the hardware. And this application goes a little bit further than just measuring simple loads or single applications. It's a combination of multiple applications. It's rotor blade monitoring. It's monitoring of the airframe. It's also landing gear monitoring, and it also it all is combined in a single system. And one of the candidates for the interrogator device is shown here. It's the X-Gator. It's a standalone system. It's a multi-channel system. It has an integrated mini PC. It has a battery pack. It has a specific data protocol that is compliant with data acquisition systems like from Curtiss-Wright that are frequently used in aircraft test applications. And in this case, it also passed a number of heavy shock and vibration tests according to the DO 160 norms for rotorcraft. And this is an example of how the integrated photonics chip technology can be used for harsh environments and for heavy applications. I also mentioned something about EN 9100. That's the aerospace certification quality system that we need if we want to produce products for aerospace. Same as for the overheat detection system, and in this case we are planning to get this certification in 1 or 2 years, which allows us to really produce systems for this market for operational use. Another example is extreme dynamic loads monitoring. It's an example of one of the many research programs that we do where we investigate the possibility of using fiber sensing for various applications in aerospace. And typically that regards structural health monitoring, where we look at damages, impacts, also load monitoring on structures, and in this case, extreme loads monitoring. And with extreme loads, you must think about the large deflections that can happen at aerospace structures, which we need to monitor. And at the same time, small vibrations or low amplitude vibrations, if there are any on that structure during operations. Now for that, we developed a system, the Supergator. It's a small chip-based device with a 1 megahertz sampling capability. And in this case, the pictures that you see there is a test that we do to correlate the performance of these fiber optic sensors with piezo technology. And what you can see in the picture below is that the yellow graph shows the results of the piezo monitoring system, and the red and blue shows the graph of the fiber sensing system. And what's interesting to mention is the fact that since piezo technology is an active sensing technology and fiber optics a passive technology, it also allows us, next to dynamic events, we can still measure passive events. And that's a very important advantage about piezo technology for these types of extreme loads events. Now we're still developing this system. It's being used in a lot of experiments for damage and impact detection and loads detection, and we plan the commercial off-the-shelf product for that in 2022. Okay, so next to aerospace, I just would like to mention 2 other examples of the work that we have done and doing that relates to our relationship with Taiwan. Well, you have seen Type A 101 mentioned a few times before in relation to other sensors. We as well have implemented there a fiber sensing system where we put fiber sensors, fiber break ratings on the 4 main pillars of the building. And likewise, we detected during this larger earthquake in March, we demonstrated that we could easily pick up the effects of this earthquake on the structure. One nice add-on is the fact that it's a system that is operational. We can access it remotely from the Netherlands. So whatever analysis we want to do, we can immediately tap into the current situation of the system. Another area is railway monitoring. Just briefly want to mention it. We have a collaboration that we organized with a Dutch company that is very active on the railway market and already has some activities with the Taiwan Railway Association and installed systems for hot wheel detection and planned systems for wheel impact, load detection, and weighing in motion, etc. All these kinds of applications that are custom to railway monitoring. And also in this case, similar to the aerospace, the small-sized, reliable modules, cost-effective, are very interesting for railway. The railway typically has a large network of track, and the benefit of cost-effective devices is enormous in this case as well. So then the products, about our vision, how we see this developing. And next to the OEM type of developments we do for aerospace, which are very dedicated systems for specific applications, we have a general roadmap where we anticipate a volume market more and more. A little bit of history. In the early days of Technobis, when we just started with fiber sensing, we built a free space optics device called the Nemesis. And in around 2011, we started to use the integrated optics technology. And we did that on a request of a company called ASML in the Netherlands, a semiconductor company. And they needed a sensing device that was cost effective, but still high performing, extremely high performing in resolution measurements, in high resolution measurements. And we managed to do that only with an optical chip, where the conventional technology of free space optics was not capable of doing that. And in the laboratory, we managed to detect wavelength shifts in the order of attometer. And that's one of the big advantages of optical chips. They are small, so you can stabilize them mechanically and thermally, and make them sensitive in that way. Now, in the years to come, we experimented a lot with products, specifically for aerospace in this case, as you can see here, and nowadays we are working on system in a package, which basically is a module that can be integrated in your own system. It's small, it's reliable, and it's cheap. And we anticipate the prices go down per system, the cost of sensors go down, while the units of the volumes are going up. And it's of a specific interest to, for instance, markets like automotive and medical. Okay, so that's about the vision. We have a strategy. We're developing our technology in 4 generations. We have had our first generation as the free space optics. Then we started to develop generation 2 with the standalone desktop systems. We call the systems Gator systems. Nowadays we are in generation 3. Which we launched for high volume medical applications, railway, wind turbine, road monitoring, pipelines, and so on. And the next step would be generation 4, which we just started. And this is really about extremely low cost standalone devices of the size of a USB stick or a matchbox. And applicable to high volume markets like medical disposables for guide wire and catheter systems, automotive battery measurement systems for thermal management in electric vehicles, perimeter sensing, data centers, temperature monitoring, but also security, and so on and so on. So we are really anticipating high volume in this case. So just to give you an idea how that looks, I mentioned the Gator, I mentioned the OEM product for aerospace, for landing gear sensing. It's an aerospace compliant implementation. We have the modules for aerospace, the OEM modules, the chip modules. Then we have the standalone units, the X-Gator as an example. And now we are working on the OEM Gator, as I mentioned, and the monod Gator. And just to give you an idea of the size, it's like mentioned here, it's really matchbox size and even smaller than that. Extremely miniaturized, reduced power usage, wireless data transfer options, really reduced costing, which is very important if you are entering the high volume markets where the margins are very small. And every increase in cost has an enormous impact. So with that, I would like to conclude my slides. For us, it's all about volumes and industrialization and module development. And the applications that we serve, we do with partners that have an interest in high performance systems. Thank you.
Okay, many thanks to both speakers. I see we have already some questions again. Also, to the other participants, you can still ask the questions. I will come back to them if I see questions. I see already one question is about the presentation of ARS navigation. And that's about more in general collaboration. Where are you looking for? I mean, also, do you look for specific companies with whom you would like to work? Also, of course, related to the Netherlands, which kind of contact are you looking for?
Okay, good question. Actually, so far, only generally. And for a small company like us, we need to do things step by step. So we welcome any cooperation, any type of cooperations.
Okay. Sorry, another question I have is also to you. If you're looking into these high-end applications in airplane, long distances, high accuracy, which is needed, do you also see other applications, for example, drones and so on? And is there an importance with the mass of the system related to the applications?
Sorry, I didn't hear quite clearly. So,
okay.
You mean like the application in drones? I think it depends on the payload. Either there's high security or cost issue price. I mean, if the payload is very high price, then it would incur like a security requirement. And those type of drone may be our target, maybe it's our application target. But the small drones, I don't think they need high performance gyros.
Okay. Another question, which I don't really understand because it came from the audience, and there is a question. I will read it. Can you please elaborate on the weighting in motion tech? A lot of benefits and user applications.
Yeah, I guess that would be for me. It's not aerospace related. It's related to railway monitoring. And well, to elaborate on that, I mean that we could say a lot about that, but in our case, this relates to the fact that we can provide these reliable, small-sized, cost-effective modules. It's about the collaboration that we have with a company that we know for a long time, and which is very much affiliated and experienced in the world of railway monitoring. They provide the complete solution, which includes not only the hardware, but also the data management system and the analysis of data, and the presenting of this data to the stakeholders through cloud systems, cloud-based systems, or other types of solutions. And our part in that is the delivery of the fiber sensing modules. And the benefits is mostly also on the fact that fiber optics is a sensing technology that is not sensitive to EMI and can be isolated from the harsh environment quite well. And that's what's the case in railway monitoring. Monitoring alongside railway tracks is quite a harsh environment, and the whole benefit is in the use of these devices. Now, what that specifically means for weighing in motion is just one of the applications where we use the fiber optic sensing or the sensing technology to put fibers on the railway tracks, basically. and measure the loads that are detected from passing trains. And these loads can be used, the data that you acquire during these measurements can not only be used to weigh the or to monitor the weight of the passing trains. It can also be used to monitor or to analyze the balance of the axles on the tracks, and also temperature of the systems passing, and for instance the quality of the roundness of the wheels in due time, due to imperfections in the railway tracks or to dirt on the tracks. These wheels tend to get damaged, and they call it they are becoming a bit square, and this squareness can be measured also by these optical sensors.
Okay.
So it's one of many applications that can be served with these systems.
Okay, thank you, Rolf. We go now to the last session. Again, due to time, we should a little bit look to the time. The last session, it will be more in looking forward to all kind of other applications, new applications. And again, two presenters, Rob Jansen from TNO and Professor Shien-Kuei Liaw from NTST.
Okay, thank you for introducing me, Eddie. Good afternoon to all of you. My name is Rob Jansen. I work for TNO, and TNO is a Dutch research organization. In my presentation, I will try to keep it short. I will first have a short introduction of the role of TNO, and then I would like to touch upon 3 fiber optic sensing principles, but because of time, I think I will only discuss 2. TNO is the mission of TNO is that we connect people and knowledge to create innovations that boost the competitive strength of industry and the well-being of society in a sustainable way. And we actually have 3 roles. One is that we work together with universities and partners in so-called public-private partnerships. So you can think about national programs or European-funded programs like Horizon 2020. We do just contract research, and we have designated tasks by the government. In order to boost the development on specific technology, on specific technologies, TNO created so-called joint innovation centers. And below, the joint innovation centers are shown that are currently active within TNO. But I would like to very briefly zoom in on the Dutch Optic Center, and that's actually a collaboration between TNO and the TU Delft University. And that Joint Innovation Center focus on the 6 markets shown here on the right. Like I said, in my presentation, I would like to touch upon 3 fiber optic sensing technologies. Thanks very much for all the nice presentations. And what you see that in most of the presentation, people touched upon using fiber Bragg rating sensors or fiber integrated photonics. And actually, we can differentiate 3 types of fiber optic sensing networks. One, which you could say is the most oldest one, is where they use a fiber optic sensor at the end of the tip. So either the light was coming out of the sensor, or they put something smart or clever at the end of the fiber. Now, currently, quite a lot of companies are offering the fiber Bragg rating technology. That's what we call quasi-distributed fiber optic sensing. So at specific locations along the fiber, you can locate a fiber optic sensor. In this presentation, I would like to briefly touch upon the distributed fiber optic sensing technology. Then the other one is chemical fiber optic sensing, because we've seen a lot of presentations where you can measure tilt, acceleration, or vibration. And I would like to tell you a bit about chemical sensing. If time allows, I will tell about fiber interferometer, which is a kind of end-of-tip technology. So distributed fiber optic sensing technology, what you do is that you make use of the impurities that are present in a fiber optic sensing cable. So that can be a single mode or a multi-mode cable. And depending on the reflection that you look on, you can measure different parameters. There are 3 different scattering regimes. One is the Raman, that's predominantly used for temperature, Brillouin scattering, that you use for strain, actually static strain, and there is Rayleigh. Rayleigh is something that they use for acoustics and vibration. Now, TNO they started to use DAS, so distributed acoustic sensing, which is again a distributed fiber optic sensing technology, in a project called GeoWell. That was a European funded project where they make use of fibers in a geothermal well. In this phase, we actually showed that we were able to build a so-called proof of prototype. And during the project, we started from what we call an ugly proof of concept phase, shown on the right, to a proof of prototype. Here on the left, the example is shown of what DAS in the end can do. So what you see is that the DAS in the end has a spatial resolution of 1 meter, and that you can measure, because you measure at high frequency, you can measure up to like 50 or even 80 kilohertz. And you can measure actually the dynamic length change of the fiber. So what it does is that along a fiber, which can have lengths up to 10 kilometers or even more, you can measure that dynamic length change of that fiber optic sensing cable. Well, here is the unit shown as we use it in the Iceland project. So we started with the ugly project, and in the end, we have a unit that we now also use for research and development, because with this DAS unit, we have full control in, for example, tuning the gauge length, the sample pulse frequency, sampling resolution, and the laser pulse width. Here below, I made a copy of the spec sheet of the DAS unit, and there you can see that the sensitivity is quite good. So we go roughly between 0.1 to 2 nanostrain. And if you look on the left, for example, if you sample, if you have, depending on the fiber length, and a gauge length of 10 meter, and sample frequency of 10 kilohertz, you have this kind of resolution, roughly of 0.1 nanostrain. So this is a new kind of technology, and how do we use it? One is for using, for example, dynamic load measurement. So in this case, we embedded a fiber, and here you see a concrete slab, and this concrete slab, we could actually move, in this case, a concrete block. It was done by hand. And the presenters before shown examples of what they call weigh in motion. And what we also did in this project is that we actually measured the concrete block moving over this concrete slab. So what you see here is, over time, we could see the movement of that concrete block. So DAS can be used, for example, for weigh in motion. DAS can also be used for vibration measurement. This is an example of a concrete bridge in the Netherlands. And in this concrete bridge, again, we glued a fiber below the surface of the deck. And then we did FEM calculations, and we actually measured the what we did is the dynamic length change of the fiber were translated into vibrations. And those vibrations were compared with the FEM calculations, and they showed a good match. And those results have been presented on a paper last year. Now, the same thing you can do with distributed strain sensing. So that means that the same fiber can now be used for another unit. So instead of DAS, you can connect it to a distributed strain sensing unit where we can measure the static load. Here, the induced static load is shown. So during a night, we put several different trucks on it, and we actually compared the measured strains with the distributed strain sensing technology. And in this example, we show that we had a very good fit with the distributed strain sensing technology compared to current fiber optic sensing or just electrical sensors. And in this case, the orange line is the distributed fiber optic sensing strains that we measured at several locations. Okay, this is about distributed strain sensing, distributed acoustic and distributed strain sensing. The next topic is about chemical sensing. In this project, what we do, we make use of a coating that is chemical responsive. So we actually have a fiber, and the fiber could contain, for example, a fiber Bragg rating, and on the cladding we put our chemical responsive coating. And by doing so, we can make it sensitive to different chemical parameters. Here is a slide shown of the development that we started. We just started this development in 2008. And actually, we now, the first projects were done together with Shell, and currently we are now using it in other type of projects. And I would like to touch upon one example, which is the fresh salt water demo project. In this project, it's aimed to measure in the underground actually the threshold where there is fresh water or where there is salt or brackish water. So we want to know the interface of fresh water that can be used for agriculture or for drink water purposes. On this slide, you show where we are with the project. We have two field demonstrations, and this is a well close to Amsterdam, which is about 100 meters deep, where we put our, we call it Foster sensors, which actually measure the total amount of salts in the water. Here's an example shown. So in this project, we now installed in a well, which is around 100 meters deep, 5 sensors, and we compare them with a current available technology, which is a so-called diver. A diver is something, electrical device that they put into the well, and they need to get it out in order to access the unit. And we compared it with our Foster technology. So what you see is that you saw on the previous slide a pump going on. So when the pump starts, you actually mesh up the freshwater level. So there is salt water at the bottom, and at the top there is fresh water. But when you start pumping, you make everything salt. So what you see happening in these graphs is that you start from a non-salt condition, and then everything starts to become salt. As soon as you start with stopping of the pump, as soon as you stop the pump, the freshwater level recover again. And you see this happening. You see this happening at the 2 sensors at the top, the 2 sensors halfway, and 1 sensor close at the bottom. And you also see the difference. So the freshwater levels are really fast, much faster restored than halfway and even at the bottom. So this is a nice example where we indeed showed how this can be used, fiber optic sensing technology for chemical sensing. And then something that we would also like to show, instead of putting the coating on a fiber brack rating, you can also put it on the complete fiber. So here on the right, we show a fiber optic sensing cable that's coated over a kilometer of 1 kilometer, over 1 kilometer. And this fiber optic sensor has been coated with a chemical responsive coated fiber for relative humidity. Now in this case, we did a test where we changed the relative humidity from 30 up to 100%, and we actually evaluated two different types of relative humidity coatings. And these are the first results shown here. Because of time, I don't go into detail. And then the last sensor is about the interferometer technology, but because of time, I will also skip that one. I would like to conclude that TNO in the Netherlands acts as a flywheel to boost innovation in different technology areas. And we're active in innovative fiber optic sensing applications for harsh environments and demanding requirements. And we work together with companies like Somni, like Optics 11, but also with Technobis. And we do have a large national and international collaboration network. Especially the Joint Industry Consortium, so the JIC on Dutch optic centers, helps us to also work internationally, and the JIC DOC also helps us to co-sponsor the two Taiwan Global Star projects where we are involved in. So thanks for having the opportunity to present this this presentation on key technologies and fiber optic sensing. Thank you very much.
Okay, then we now to the last speaker.
Okay, thank you. Good morning, good afternoon. I am Shien-Kuei Liaw from National Taiwan University of Science and Technology. Today, my brief talk is with the title of Overview of Modern Fiber Optic Sensing Technology and Application. Okay, I think the brief outline are showing below. And first I will show the brief overview, and then talk about some modern fiber optic sensing technology. And then I would like to introduce some current project and finished project investigated by my lab. Okay, this figure shows a typical layout of a fiber optical sensing system, which is shown along the detection possibility through various observed signal that can be coupled with automatic alarm and so on. So you can see either the gun fire, the digit, the vehicle, the personnel that we can observe, we can monitor simultaneously. And I think because a lot of experts and research already talk about the principle of fiber progressing and today, so let me skip this page. And for this page, it's talk about another fiber sensing system. It may be I think rather new. It's called a distributed fiber optical sensing. I think this is based on the principle of already of Raman of the Bruin cascading effect. So up to now, they have some commercial product in the market, but I think the spec and the performance and still leave much room to be improved. So you can see this the figure show in the I think in this page you can see that maybe we can have a fiber along the land and we can test, we can monitor some parameter along the fiber and send the signal back to the fiber end for a signal processing system and for the optical integration system for analysis and monitoring. And here is something like a pyrometer intrusion detection. So it is a common practice to have both the sensing put install on the fence and also on a bare cable, that to make the sensing more sensitive and more accurate for the environment to need to be monitored. And here is the page shows some concept of optical sensing in IoT. So in IoT, there you can have text many parameters simultaneous, like chemical, like acceleration, like temperature, like speed, and so on. So maybe you can use multiple wavelength WDM sensing system. Or also maybe you can use some sensor network to implement your system. And here is a technology called distributed acoustic sensing. I think this is based on the distributed fiber sensing system. So here that is some prior work. You can see that even at 70 kilometer, that the people can detect 10 narrow strand, and under the signal of only 20 dB optical signal to noise ratio. So you can detect something happen, witness the 15 meter by this distributed acoustic sensing technology. And this figure shows the concept of sensing over fiber system. So you can see we have a signal processing center, and the waveform from sensor head are transferred over the fiber. I think the fiber could be designed as a WDM skin for joint the signal processing, effective waveform transfer and cloud sensor signal processing for low cost and high performance sensing could be realized. So you can have a multiple sensor head at the same time, and they can monitor the different objective at the same time. So here is also another concept of the sensor over fiber, but this is uses the technology sensing technology in like in an airport. So the signal distribution network based on still based on the optical fiber. Maybe you can have fiber to have a router, have a wide fiber to like a networking sensor system to detect all the whole airport, and sensing the whole airport the airport condition. Okay, and now I think for the topic that I go to just to introduce three samples of the just finishing and ongoing project at my lab. The first one is fiber propagating based switching system. I think this is a 3-year project that supported by the National Center of Research, National Center of Earthquakes, research on earthquake engineering. In this project, my lab developed some data logger or some data logger here. So we developed a kind of a laser-based fiber laser-based source instead of ASC source, so we can have a much more dynamic range compared to a traditional commercial product of the data logger. And we use such kind of data logger to simultaneously monitor several bridges simultaneously. And then we send back the data to the central office for the data monitoring and data NSI calculation. And here that you can see the guy who wore the red coat myself. That we have tested our data logger system under a super highway, and you can see the working office over there. So the spec so far is quite matched to the commercial product, but I think the cost should be about one over third of the commercial product price. It's very I think it's very have a very good CP value. And for the second one is my lab do some research on the simultaneous multiple parameter sensing using fiber grating. So you can see these two pictures is the homemade sensor head. One is use the fiber grating sensor head, and the other is use a long period fiber grating sensor head. And here that you can see the configuration. So this is also based on the fiber laser configuration. We have a short period fiber grating for to determine our lasing signal, and we have long period fiber grating just to show a central dip to do another parameter. So you can see that we in this figure that in the configuration we use some equipment like OSA, and we also use some component, WDM component, fiber grating, and urban dome fiber and pump laser here. And you can see, okay, you see the spectrum. You can see the peak is induced by the fiber grating, and the dip is induced by the long period fiber grating. Since the long period fiber grating is more sensitive to temperature and to the repair index change, while the short period fiber grating is sensitive to water level, so we can simultaneously test the water level and temperature, or water level and repair index simultaneously. But basically, one fiber grating to monitor one parameter, and I think the accuracy is I think more than 95%. Because just have some error, but the error can be offset by a very simple 2x2 matrix to do some offset and to obtain a very accurate result. Okay, the final is another project which was supported by the ITRI in Taiwan, that we developed some BOTDA optic fiber sensing system. I think this kind of system is I think would have a very good potential to be used in carbon capture and storage world with oil and gas pipeline or in underground pipeline to do some in-time monitoring. So maybe people remember that in 2014 that underground gas the link result in explosion in Kaohsiung City in South Taiwan. So I think the technology is very important to develop, because people don't know maybe 10 or more than 10 kilometers away where would have something happen at any time. So you need such a technology to do environmental monitoring. Maybe it will be more useful than fiber grating point-to-point monitor system in this case. Okay, and this is some setup, but nowadays that we try to improve the system little by little. So we can see that I have quite a few equipment here, just like a pattern generator, just like a signal generator, like a EOM, or like a optical tunable filter, and so on. But we try to simplify and to modify the skin. And you can see this is the setup. I think the photo was taken about 2 years ago. So nowadays that we have integrated some of the equipment together, so the total size are small and small. It becomes more and small, and we hope someday it could be a portable one, integrate two or all-in-one to be portable equipment. And here that you can see that we show the 2-dimension Boolean frequency for the distance monitor and the 3-dimension system here. So now so far that we can monitor about a 2 meter parameter happen under 15 kilometer long distance environment. So I think this record, I think not a very good record if you compare to some leader group in the world, but we believe that the record could be improved very fast, because for the past 2 years we have shortened the resolution, spectral resolution from 20 meter to 2 meter today. So that's for the 3 project that I just have to give a very short introduction to the status of my lab research. So we are welcome to have any industry academic collaboration project and some collaboration. Thank you all of you. Thank you.
Okay, thank you very much. We're running a little bit out of time, but especially to the last speaker also, Professor Shien-Kuei Liaw.
Yeah.
I see many applications. Are you looking also to some special areas in which you would like to see new collaborations, for example, with the Dutch people?
I think in domestic in Taiwan, I have quite a few potential company that have interest in to have a collaboration with me, but I'm very interested to have a collaboration with with your country, with our company. Yeah.
Okay. Okay, we can look into that later. Yes, one question to Rolf. You had also an application of chemical sensing, and you very fast it was together with Shell. Are you also looking into measuring oil spill?
Yes, oil. Yes, correct. So oil is still an interesting application. However, what you see with the market going on, there is not much request from oil and gas companies to further develop that. So yes, it can be used for oil and gas, but what you actually actively now see is that they either want to use it for carbon dioxide monitoring and storage, or that we now more focus on using one of the principles that we developed in the project, like the freshwater salt project. So originally it was developed for monitoring the presence between brine and oil, but now we just more focus onto brine, which then brine is actually salt water.
Okay. Yeah, so I'll keep to these two questions. I want to make one final remark, two final remarks. The first, it was in the beginning said, or as a question, are there possibilities for funding, like Global Stars? I said that's a difficult question because that's funding for the companies, but I want to address that we are aiming at a fourth session. This is the first session, but the fourth session in which we are looking at a research call together with the Netherlands and Taiwan. The National Research Foundations in the Netherlands and in Taiwan are both working on that. So there will be a discussion about the funding, and that will be in the fourth session. Only the planning of the fourth session is not yet clear. So the first three sessions are now in the coming 2 weeks, and the fourth one will be a little bit later. So that was a general remark about funding. At the end, I mean, I want to thank everybody to be present. I also want to tell that next week, the same time, there will be the second session. The second session will be on integrated photonics, and especially on the applications of integrated photonics. So again, I mean, if people would like to be present, you're welcome to again sign up, and next week we will continue on this topic. And again, many thanks to everybody. We run a little bit out of time, but yeah, good luck until next time.
Thank you, Chairman. Thank you.
Indeed, thank you very much. Bye-bye.
Thank you.
Thank you. Bye-bye.
Thank you. Bye-bye.
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 Bye.